Swayam Prabha. Digital India. Educated India.
So, in today's lecture, we will take a few examples based on what we did in our previous couple of lectures. That is the basic principle of mass transfer. So, if you recall, we derived a general expression for mass transfer by diffusion. So, essentially we had two terms for the molar flux. One was by the bulk transport from one location to another, and the second was a term due to fixed diffusion. That is the molecular diffusion, as observed by the observer who is moving with the bulk velocity, and we also did define the bulk average velocity of the fluid. So, we had two special cases. In one was when then fluid medium is stagnant, and the second one we had when we had equimolar counter diffusion, and we said J equals minus JB, or so based on that we simplified N equal to minus NB, and then we simplified the expression for molar diffusion flux. We integrated and we got the expressions for Na, Nb, etc. So, we take a few examples into the lecture, couple of examples that will essentially elaborate. So, let us take this example 1. So, what we have here, we have two planes, say 1 and 2, binary mixture of oxygen and carbon dioxide. Okay. Let us assume the pressure is given 1 atmosphere 10 to the power 5 Newton meter square, and we have temperature 0 degrees Celsius or 273 Kelvin, and also given that binary diffusivity of A and B, or oxygen and CO2, it is 1.787 10 to the power minus 5 meter square per second. The question here is that this carbon dioxide CO2, say it is stagnant. So, when we say CO2 is stagnant or non-diffusing, essentially we are saying that Nb equal to 0, and the question is, due to a concentration gradient or partial pressure at plane 1 13,000 and at plane 2 P2 equals 6500 Newton per meter square, we are interested in finding this diffusion flux of Na in terms of say kilomole per second per meter square. So, it is a very simple example, the first one to start with, and we start with our expressions for Na, which we developed in our earlier class. So, we have Ya, Na equals Ya n, which is Na plus Nb, minus Dab dCA over dz. So, this was our first governing equations for diffusion flux. Since Nb is 0, we have simplified expressions. We can always convert write Ca in terms of partial pressure as Pa over RT. So, this Ca can be substituted and one can integrate this equation. The idea is that either you start from here, or you start from the integrated equation which we had brought and we had simplified earlier. So, we go back to our previous expressions when we are integrated between 1 and 2 and obtain the relations for diffusion flux. So, on integration one can show that we will get Na, Dab, total pressure, RT, Z, ln P2 minus Pa2 over Pt minus Pa1. So, this is on integrations which we did in the previous lecture, and we can start from here also. So, all we have to do is right now to substitute all the values for whatever numerical values we had here, which is 1.87 10 to the power minus 5 for diffusivity, total pressure 1 atmosphere 10 to the power 5, gas constant R 8314. So, this unit would be Newton meter per kilomole Kelvin. Temperature is given 0 degree Celsius or 273 Kelvin, and we had this diffusion length, the distance between the two plane at Z between 1 and 2 as 2 millimeter, which is 0.002 meter. So this 0.002 into ln, Pt is the total pressure 10 to the power 5 minus partial pressure at location 2, which was given as 6500, total pressure 10 to the power 5, and we have partial pressure at 1, which was given as 13,000. Okay, so all we have to do is to substitution and solve to obtain 2.968 10 to the power minus 5 kilomole per meter square per second. So essentially this example is the most simplest example, in which case we have assumed that the bulk medium or Na plus of Nb in which Na diffuses is a stagnant. So we had Nb equal to 0 and we substituted, we had two components, then we integrate to obtain this simplified expression for diffusion flux. Okay, we will take slightly more complex examples in which in the same plane 1 and 2 Na diffuses, and then when it reaches the second plane, there we assume that there is a heterogeneous chemical reactions. So A gets converted say into B, and then B diffuses back to this diffusion medium. Okay, so essentially still we have binary mixture of A plus B. Now if you recall what we did in the previous classes, previous lectures, we made certain assumptions. We said that first, steady state. So whatever expression we used that time, and even today's in the first example, we had a steady state. That's one. Number two, we said that there is no chemical reactions, which means the plane we are considering, the diffusion plane of 1 and 2, there is no chemical reactions. In this example, we will see that there is a chemical reaction at the surface. That's all right then. Still we can use the expressions which we obtain for a steady state and no chemical reactions. So this example 2 is a simpler example, but still it's slightly different from what we did in the minutes ago. So let's get back to this example 2, where we have two diffusion planes 1 and 2, and now we have carbon monoxide which diffuses in this directions. Okay, concentration of carbon monoxide here it's given, it is 60%. So we say that Ya1, A for carbon monoxide, is mole fraction is 0.6. Okay, and when carbon monoxide reaches plane 2, then there is a reaction. So we can assume that it's a heterogeneous surface which is say coated with nickel. So what we have, CO plus nickel giving to nickel carbonyl, CO4. Okay, so your balance is 4CO plus nickel. Now this product of nickel carbonyl, this also diffuses back into this. So we have now B of nickel carbonyl 4. Okay, so the more important here to understand that we have binary mixture of A and B, carbon monoxide diffusing from 1 to 2, and the product diffuses back into this bulk mixture of A and B. There is a chemical reaction, but the reaction takes place at the plane 2. That's more important. So in this A and 2, between 1 and 2, this diffusion medium of del Z, there is no chemical reactions. We can still assume a steady state, no chemical reaction, and apply the same expression which we obtained earlier, although the reaction takes place at the boundary, not within the homogeneous system. Okay, so now we go back and we apply the physical properties of all this. The system is given DAB of carbon monoxide in nickel carbonyl or nickel carbonyl in carbon monoxide is given as 1.91 10 to the power minus 5 meters square per second. This gas film, if you call it this binary mixture of gas film between 1 and 2, all right, del Z is given as 2 millimeter, which is 0.002 meter. Okay, now the concentration of 1A is at the location 1 in the bulk medium is given 0.6, and the rest is YB1, which would be 0.4. Now if you notice here that A diffuses in this directions and B diffuses in the reverse directions, and if you go by the stoichiometries, we have 4 molecules of carbon monoxide reacting with 1 at the surface. This nickel is at the surface to give back this product B in the stoichiometric ratios of 4:1. So the question is number 1. First question is calculate the rate of formation of the compound, which is here nickel carbonyl CO4 per unit contact area. So this contact area is nothing but the plane 2. Okay. Before this, or we can also calculate the flux of Na and Nb. You will see that all of this is well related to each other. Okay. Before we make any other assumptions or restrictions, let's let's start with the same expressions which we obtained for molar diffusion flux of A and B. Okay. So we start with the same expressions. What we had, Na equal to Ya Na plus Nb minus Dab dCA over dZ. Since it's a gaseous mixture, it's not a bad idea to convert this Ca into the partial pressure, Pa by RT, and we can also write this as a mole fraction, Ya total pressure over RT. Okay. Now the question is that we are trying to solve Na, and we have one more unknown, which is Nb. In the previous example, if you recall, we had stagnant B, so we could substitute Nb equal to 0. Here we have Na diffusing in one direction and Nb diffusing in the opposite directions. Okay, so both are unknowns, both we are supposed to calculate. So all it means that we are looking for one more expression or one more equations to make the problem well defined. Now if one has to go back to this stoichiometry to see that one molecule of nickel reacts with 4 molecules of carbon monoxide to form this product B, which is nickel carbonyl. That means we can apply the stoichiometry here. Okay, so if you apply the stoichiometries, then you should obtain Na equals minus 4 Nb. So when we write these expressions, there is of course a stoichiometry involved here. Okay, but more important here is that if you recall in the previous lectures, everywhere we are assuming that we have a steady state. That means concentrations anywhere between 1 and 2 does not change with time. Now look at very carefully. There are two rates here. One is the rate of diffusion of A and B, and the second is the rate of chemical reactions at the surface. So when A arrives, there is a rate, finite rate, at which A gets converted to B, and then this B has to diffuse back. So when we assume steady state, again we have to qualify by saying that reaction A to B is very fast. In other words, it's not a rate limiting, and what is limited here still is by diffusion. Then we can write Na equal to minus 4 Nb by stoichiometries, and we say that assume steady state or assume fast reactions, so that we can assume steady state. It's also a quasi steady state approximation because there are two rates. One is the rate of diffusion and the other is the rate of reactions. We are assuming that the reaction is very fast. As soon as A arrives, it's forming to B and B diffuses back. So still we are looking at between medium 1 and 2 where we have a steady state and there is a reaction at the boundary which is very, very fast. Okay. So without restrictions, we write Na equal to minus 4 Nb. Of course, we bring this stoichiometry here, and then we solve this equations. So now once we assume Na equal to minus 4 Nb, all we have to do is to substitute in the previous equations. Na equal to Ya Na, and Nb is Na over 4. The minus sign signifies here the diffusion flux is in the opposite directions. Minus Dab, we go back and substitute Pt, Rt, etc. to make it Dab over Rt. We have dPa over dz. Now we can integrate and solve for this Na, molar diffusion flux of Na here, which we did it in the previous class. So the idea here is not necessarily every time you have to go back and start from the first principle. You can also start from alternatively you can start from integrated equations, and in that equation you can substitute Na equal to minus 4 Nb. So we like to go back to the previous equations which was integrated in terms of for Na in terms of Na, Nb, and it was implicit of course in terms of concentrations, but in that equation also we can substitute this stoichiometry and then we can solve the problem. So let us go back to the integrated equations which we had earlier obtained as Na equal to Na plus Nb, dAb C by Z. So instead of C we write Pt over RT Z, ln Na over Na plus Nb minus CO2 over C, Na over Na plus Nb minus Ca1 over C. So this is the integrated equations. Okay, we can start from here if we remember, or we can go back to the original equations for Na1 expression governing equations, and then we can integrate after substituting that the Na equal to minus 4 Nb. Either way it will work. Okay, so this you should try as an exercise both ways, so that you realize that you have not made any mistake in this numerical integrations. Now we can substitute Na equals minus 4 Nb in this integrated equations. Then we have Na over Na, Nb if we remove we have Na over 4, dAb Pt over RT Z ln Na over Na plus Nb. If we substitute we have now 4 by 3. Cat by C is nothing but the mole fractions at location 2, and we have 4 by 3 minus Ya1. So we have Na over Na minus 4 Na by 4. To make it 4 by 3, dAb 1.91 10 to the power minus 5, total pressure 10 to the power 5, R 8314 same SI unit, temperature 313 Kelvin, diffusion length 0.00, ln 4 by 3 minus 0 over 4 by 3 minus 0.6. So let us make a note here also. We are assuming YAT equal to 0 or approximately 0, and here as we said earlier there is a restrictions why we are assuming y mole fractions of A at this surface, catalytic surface 0, and the reason is only one, that it is a very very fast reaction. As soon as A arrives it is getting converted into P. So the mole fractions of Y at the surface is 0. All these different assumptions which we are making, it's quite important that we note, and when we apply any expressions we try to realize that at what point, at what step we have made those assumptions. A steady state, all right, when we say it's a steady state we must ensure that all the other rates, if they are there, they are at quasi steady state or very fast. So here we have two rates, one is the chemical reaction rate and one is the diffusion rate. Chemical reaction rate is very fast, then only you are making this steady state assumptions. Mole fraction of A at the location 2 0. Why? Because it's a very fast reaction. Na equals minus 4 Nb. Why? Because there is a stoichiometry. The moles of 4 molecules of carbonyl CO carbon monoxide gives 1 mole of products P. So with that restrictions we have simplified this expressions and we have obtained an expression for Na in terms of all quantities known. So that's why this Ya2 is 0 here. So after substituting this, all we have a numerical numbers of Na equals 2.925 10 to the power minus 4 kilomole per meter square second. So that's the first part or the second part of the question, that calculate Na and Nb. Once we have Na, we can calculate Nb as Na by 4 to make it 7.313 10 to the power minus 5 kilomole per meter square per second. Now the question here was, what is the rate of formation of B. That was the question. At what rate B is formed, and what we have calculated, at what rate B diffuses between 1 and 2. So at any location between 1 and 2, the diffusion flux is kilomoles per meter square per second. And now we are saying that since the reaction is very fast, steady state, whatever flux we have at any location between A and B is the same as what we have at the surface. There is no lag there. It's all because of your assumption of a steady state and the reaction being very fast. It's very important that we understand the physical meaning of these two assumptions and see how do we obtain this rate of products. So NB, with what we obtain here, is nothing but rate of production of B. So they have the same answers. One more example we will take here, that's for a stiffened tube. Okay, so that's a bit more complex. So we have 1, 2, 3, and this is about a stiffened tube. If you recall, a stiffened tube, it's a very simple tube, tubular arrangement, which is used to estimate or measure the diffuser coefficients of B, of A in B or B in A. So essentially what we have a tube filled with certain organics, acetone, ethyl acetate, whatever we have, whose diffusion coefficients we want to measure in B as it evaporates. So we have the schematic in mind, that this organic vapor evaporates, it diffuses, carried by this air on the top of it, and then it develops a concentration profile. Within this, we have to make some measurements, how much amount of this organic is evaporated over a period of 8 hours, 10 hours, 24 hours, and then we estimate this diffusion coefficients. So we take this example of this stiffened tube, very popular example here. So we are talking of this stiffened tube. So what we have, a very simple U tube. Okay, it's filled with acetone. So the problem reads that this guy is filled at till 7.5 centimeter. So we have ethyl acetate filled in this tube, okay. Temperature, pressure is given P 1.013 bar. Temperature is given as 298 Kelvin. DAB is given as 0.0866 10 to the power minus 4 meter square per second, and total height of this tube is 15 centimeter. So half of the tube is filled with ethyl acetate, and ethyl acetate evaporates. The rate of evaporation will of course be decided by the temperature, and at this temperature vapor pressure of ethyl acetate is given as 0.1264 bar. So ethyl acetate evaporates, and here we have a very gentle stream of air. Okay, so again there are several restrictions here, right? You have to look at carefully to ensure that whatever expression we have developed, one expression, how do we use it and under what assumptions we are using it. So we don't have to violate any restrictions of a steady state, all right, stagnant medium B, NB equal to 0, or we have equimolar counter molecular diffusions, or we have non-equimolar counter molecular diffusions, Na and NB. So we have to look at those restrictions, and then we have to apply these equations. So let's see that where we apply those assumptions. We have been asked to, as it evaporates, it's swept by this air. The question is, how long will it take for the level to drop from at t equal to 0 from this 7.5 centimeter to drop to another 0.5 centimeter. In other words, H0 to start with is 7.5 centimeter if you measure from the bottom, and we have final, it drops to make it 7 centimeter. Okay, so these are the two restrictions from here. That question is how long will it take for this ethyl acetate level to drop from this level to this level. Now it drops because ethyl acetate evaporates, it comes to this air and air is swept. So we can assume if quantity of ethyl acetate is very small which evaporates and very large amount of air, that mole fraction of Ya2, A is for ethyl acetate and B for air. So the mole fraction of ethyl acetate at the outlet of the tube is approximately 0. Okay. Question is of course number 1. First question is what is the molar diffusion flux at T equal to 0? So at T equal to 0 when the level was 7.5 centimeter, half filled, what was the molar flux? So when you have these questions, that means molar flux, it changes with time. Okay. So if you recall the expression which we developed, it's meant for a steady state. We assume that there is a steady state and then we obtain the expression for diffusion flux. Here the question is at T equal to 0, what is the diffusion flux? That means after some time this diffusion flux is going to change. So it's dependent on time now, right? So you have to assume, you have to be very, very careful how and when or if we can use that expression for diffusion flux of Na. So that's the number 1 question. Question 2, as we said, how long will it take? How long will it take for the level to drop to 7 centimeter, measured from the bottom of the tube. So now let's revisit this tube. Here the level decreases with time. So first we have the level here, now it decreases here, and every time there is evaporation of ethyl acetate here. Okay. So it's quite important that we also understand what would be the expected solutions, okay, before we solve numerically. We have a level of acetone, ethyl acetate, which is 7 centimeter, and on top of this we have 7 centimeter of empty space or filled with ethyl acetate and the air. Okay, so 7 centimeter and 7 centimeter. Then this level decreases. Mole fraction of ethyl acetate at the exit of the tube is 0, and at the surface is determined the vapor pressure. Now temperature is fixed. If the temperature is fixed, vapor pressure is fixed, atmospheric pressure is fixed, concentration of ethyl acetate at the surface will also be fixed. But look at the gradient. Concentration gradient, profile of the concentration gradient will keep on changing. Why? Look at this profile here before we solve. This is 2 here and this is 1. This is 7 centimeter and we have 7 centimeter of ethyl acetate to start with. Concentration here is 0 because we assume that as soon as vapor of ethyl acetate comes here, it's swept by this flowing air. Concentration here Ya1 of ethyl acetate will be P0 over the total pressure, PT, PA over PT. One can calculate this. P0 is fixed, total pressure is fixed. If these two are fixed, then we have some gradient like this to start with, and when the level drops, it's still 0, and this concentration level is still fixed here. But look at the profile which has changed here. After some times the level drops here, this is 0, this concentration is still fixed, we have another gradient. So gradients, concentration gradient or concentration profiles change with time. And the question was asked, that's why at Na at T equal to 0, what happens? Now let's start with expressions which we obtained to see how we can apply or to apply that equations, what are the restrictions, what are the assumptions we are making. So the expressions for Na is Na equals Ya Na plus Nb minus Tab dCA over Tz. First thing here, problem statement reads that assume air is stagnant. So between 1 and 2 we are assuming that air is stagnant, which means we write Nb equal to 0. Now when we say Nb equal to 0, the more important here to note that Nb can also be written as Yb in A plus Nb minus Dab dCb of Tz. Okay. Of course, if we make Nb equal to 0, it's easier to integrate these equations and obtain what we obtained earlier, what we get earlier. But more important is, let's note down physically what does it mean that Nb equal to 0. Air is stagnant, so this term is 0, but we have convective transport here, bulk transport here, which is Yb Na minus, and then we have the second term minus Dab dCb by Tz. So what it means, air still diffuses. As ethyl acetate diffuses in this direction, air diffuses by molecular diffusion, but air is insoluble in ethyl acetate, which means there is an induced bulk transport in this direction, so that the transport of air by Yb Na is same and equal to opposite to this molecular diffusion of B. So although overall Nb is 0 as seen by the stationary observer, there are two components. One is the bulk transport and one is molecular transport for both A and B here, molecular transport given by this Fick's first law. So we do have a gradient of air which goes like this in this diffusion length between the top of the surface, top of this tube and the top of this ethyl acetate surface. But at any instance, whatever amount of air is diffuses by molecular diffusion, it's balanced by this bulk transport in the opposite directions. So this diffusion in this direction is balanced by this bulk transport, and we have a stagnant air in the medium. So that's what the meaning of this, air is stagnant. A stationary observer sees air stagnant, no molecules of B diffuses or moves in one direction, either from 1 to 2 or 2 to 1. But if the observer moves with the bulk velocity, he will see air diffusing in the directions opposite to the ethyl acetate. Right. So that's very important that we understand the physical meaning of each and every term which we address in our first, second or third lecture. Okay, let's get back to this problem. So that's the meaning of Nb is equal to 0. Now we substitute here to obtain Na as Ya Na, Nb is 0 minus Dab, we can write Ca in terms of partial pressure and Tab over RT as d partial pressure of A over this Tz. One can integrate these equations, but already we have integrated our previous expressions to obtain Na as Dab total pressure over RT Z ln Pt minus Pa2 over Pt minus Pa1. This Z is diffusion length. Now look at this problem. We obtain this expression for a steady state. So that means diffusion flux Na does not change with time. Okay, and here we see that expression that Na depends upon Z, but Z itself is a function of time, which means Na is also a function of time, because all the rest of the quantities, they are fixed. Pt, Pa2 we can assume 0, Pa1 partial pressure of A is nothing but the vapor pressure of ethyl acetate, temperature is fixed, all quantities are fixed. If Z changes with time, Na will also change with time. So the question here was that what is the diffusion flux at the instance when the level is 7 centimeter. So we have essentially Na t equal to 0 equal to, all we have to do is to substitute and put the correct value of Z t equal to 0. So we have DAB as given as 0.0866, total pressure 1.013 10 to the power 5 divided by R 8314, 298 into Z, which is 75 centimeter. This is 0.075 meter. Ln 1 minus 0, if we divide by PT, 1 minus vapor pressure is given 0.1264 divided by 1.013. So the vapor pressure of PT0 is given at that temperature is 0.1264 bar. So we have this, all we have to do is to substitute and solve to obtain 6.292 10 to the power minus 7 kilomole per meter square per second. So the diffusion flux to start with t equal to 0 is so much, and as Z increases, Na will decrease 1 over Z. So that's the first part of the questions. The second part of the question is even more interesting. So the second part of the question was, how long will it take for a level to drop from Z1 to Z2? Okay, and as we said earlier that if the level changes, diffusion flux also changes with time, concentration profile also changes with time. So in reality this is a unsteady state problem. Out of any variables in a physical system, if one variable changes with time, the overall problem is unsteady state. But we are going to make use of well-known quasi-steady state or pseudo-steady state approximations. So we also understand that what is the physical meaning of this quasi-steady state approximations and how we are applying an expression which we obtain for a steady state. Okay. Now here the level of A decreases very, very slowly. In fact, if we solve the problem, it will turn out to be that it will take 22 hours, 24 hours for the level of decrease of A decreases to some 0.5 centimeter by height. Okay. So if you have, so there are two rates. One is a rate of diffusion and one is a rate of decrease in this level of the surface. Just like try to recall what we had earlier in the previous example, where a certain species diffuses and then it reacts at the heterogeneous surface. So there we have two rates. One is a rate of diffusion and one is a rate of reactions. So whenever we have two rates, it's always a good idea to compare the rates of the two two steps. It's possible that one rate is very fast and another rate is very slow. In those cases, one can make a quasi-steady state. Otherwise, the problem makes it, if you want to solve it mathematically, it's a very, very rigorous problem. You will have to set up the two governing equations, one equation for the diffusion and one equation for the reaction rate, and in this case another rate is for the rate of decrease of this level. The two are coupled together and they have to be solved simultaneously. But if you make a quasi-steady state, which has to be consistent with the physics, that the rate of decrease of this level is very, very slow. Over that over that time step at which this level of ethyl state decreases, if we assume steady state, that means we can still apply what expression we had for diffusion flux. Okay. So assuming this quasi-steady state, that means level decreases very, very slowly, one can still apply the steady state expressions. Now if you go back to this, we have the same, just recall the tube here, and the level was says Z0, it decreases to Z1. Okay. And then we said that already we obtained that expressions that NA is Z dependent, DAB PT over RT Z ln PT minus PA2 over PT minus PA1. So when we obtain this relation, we said it's a steady state. Now we are saying that Z is also a function of time and NA is also a function of time. See, that's a place, that's a step where we have to we have to be careful in applying this quasi-steady state. And here we apply this because we said that this drop of 0.5 centimeter takes place over a very longer time, and diffusion rate here is faster in terms of the rate of decrease of this. So now if we make a material balance of over the del T, how much amount of A has evaporated, and equate with this diffusion flux. So we have Na moles per second per meter square of ethyl acetate which evaporates over this cross sectional area of A. So A is a cross sectional area over this del T. So it's a material balance. In 1 second, so much kilomoles or moles of A diffuses over this del T. Now this is nothing but how much level has dropped in this del T time, which is del Z into area. This gives you differential volume multiplied by the density of ethyl acetate divided by this molecular weight to make it moles per second. In total moles of A evaporated over del T equal to the quantity of ethyl acetate which is lost between this Z0 and Z1. In limit of del T tends to 0, essentially we have dZ over dt equals Na Ma over rho A. See the expressions for dZ by dt, at what level dZ surface changes, we are writing it Na Ma over rho C. In reality Na is also a function of time, but we are assuming that Na is quite faster at the rate of this decrease of this level. So we have again we have made use of PSSS, pseudo steady state approximations, quasi steady state approximations. Now all we do, we have two equations which are almost decoupled. We take this expression for Na and substitute here and we integrate. Okay. So if we now take that expressions and we integrate here, we will get DAB PT RTZ. So this is a term of Na, PT minus PA2 over PT minus PA1 into Ma over rho A equals dZ by dt. Now we integrate. If we bring this term here, so we have entire expressions like this. Z will come here. We have dt equals dz z dz, going from Z1 to Z2, t equal to 0 to. Now again let's go back and see where we are making this restrictions or assumption of quasi steady state. The entire rest of the terms is nothing but your diffusion flux Na, which we are writing here. And when we integrate and we say that if Na is a constant or does not change with time, then we can take it outside this integral, and that's the place we are making use of quasi steady state approximation. It's very important that we understand, instead of blindly memorizing some integrated expressions and applying here. Here, by making this quasi steady state approximations, pseudo steady state, the diffusion flux Na is a constant over this time del T, because the level changes over a very long time. We can take out this Na as if it's a constant. DAB PT RT ln PT minus PA2 over PT minus PA1 into Ma over rho A, and we have T here integration, and then we have Z2 square minus Z1 square over 2. Now all quantities are known here: total pressure, diffusion coefficients, R. This is your total time. So this is temperature here. Let's write it time. This is the temperature, total pressure. PA2 at the outlet of the tube is 0 because concentration is there is 0. PA1 is nothing but vapor pressure. which is given to us, molecular weight, density of acetone, two heights Z2 square minus Z1 square. If we see the schematics, we have the top of the level, which was our Z1, and we have Z2, which is here. Sorry, we have this Z0 and we have Z1 here. So to start with, this was 7.5 centimeter, and the question asked was how long will it take to further drop by 0.5 centimeter. This will become your 8 centimeter. So this is a diffusion length. Ethyl acetate evaporates from this surface and goes over this and swept by this air. So all these quantities are known. You can calculate this time of diffusion. So time of diffusion is T, all direct substitutions, 900, 8314, 298, 900 will be the density of acetate, molecular weight 88, diffusion coefficient 0.0866, 10 to the power minus 4, 10 to the power 5 into 2 into 0.08 square minus 0.075 square by 2, this 2 is here, divided by this ln 1 over 1 minus 0, 1 minus 0.1264 divided by 1.013 total pressure into this. This will comes out to be approximate 85071 second. So it takes a long time for this water level to level of ethyl acetate to decrease from 7.5 centimeter to 8 centimeter. Now this is the third example we had, where we applied the same expressions for Na in terms of bulk transport and the diffusion components, but here we are applying this quasi steady state very rigorously. We brought one more rate, the rate at which the level of ethyl acetate decreases from one to another. So at every step of decrease of the level, one has to assume that the other rate, which is diffusion flux, is stationary. Okay, in that case we can make these assumptions and we can integrate the equations and we can apply to find out the total time for the level to decrease. Now what we do, we take one more example which is very similar to what we had earlier. Now it's a spherical coordinates. In our last lecture we said that we can still apply the diffusion flux, the expression for diffusion flux in a spherical coordinates. However, we have to be careful that in case of spherical coordinates, the cross sectional area or the area of this diffusion plane changes with the radius or with the distance. So it's moles per second which is conserved, not moles per second per meter square. Unlike in the Cartesian coordinates, when we say that there is a steady state, Na moles per second per meter square will also be constant with time and along the z direction. In case of spherical coordinates, if we say it's a steady state, moles per second per meter square may not change with time, but it will change with the distance, because meter square changes with the distance. 4 pi r1 square, then we have 4 pi r2 square. So when we apply these equations, we have to be careful with the integrations. There has to be a r or distance dependence term which has to be integrated. And a very common example for such cases is evaporation of naphthalene ball. Okay, so what we had earlier was evaporation of ethyl acetate in tube, and then the diffusion length path is in Cartesian coordinate system. Now we have a spherical naphthalene ball which diffuses, which evaporates in atmosphere, and then a question asked is how long will it take for the radius of this naphthalene ball to decrease from say R1 to R2, or the amount of the naphthalene to decrease from W1 to W2. Okay, so it's the same principle, except now we are looking at the spherical coordinates. Okay, so let's go back to this example here, example 4, which is also very popular, sublimation of naphthalene spherical ball. So we have a naphthalene ball like this, spherical. It's given that to start with its weight is 4 kg. As it evaporates, it shrinks, and the final weight is 3 kg. So the question is same. Pressure is given, P 1.013 bar. Temperature is given 318 Kelvin. Diffusion coefficient is 6.92, 10 to the power minus 6 meter square per second. Molecular weight of this naphthalene is given as 128. Density is given as 1140 kg per cubic meter. Okay. So now look at the evaporation of this naphthalene. So when it diffuses, first it has to evaporate. So it evaporates into atmosphere, which is air. So if it evaporates, then there has to be a concentration gradient. So all it means here, the concentration gradient or concentration at the surface is controlled by the vapor pressure, or what we call sublimation pressure. It's a solid. So the vapor pressure or sublimation pressure dependent upon temperature. So the concentration at the surface is controlled by this, and concentration in atmosphere will depend upon the composition of air. If we assume that as soon as this naphthalene ball comes out of this, it diffuses and it's swept away by air, we can assume that the concentration at very far distance is approximately 0. So this problem is very similar to what we had in the earlier example when we had this ethyl acetate. The level decreases from here to here, and there is a diffusion length of del Z from here to here. Here also we have a diffusion length from one surface to the very farthest. Okay, so let's get back to this problem and redraw this schematic. So at any instance, the radius is R, weight is W, and naphthalene vapor diffuses into atmosphere. So we have different planes of diffusion. Okay, which means the cross-sectional area or the projected area or the area of this diffusion plane itself changes from 4 pi r1 square to 4 pi r2 square to 4 pi r3 square, etc. We can still go back and apply the same expressions what we had earlier here, what we obtained earlier, but more important is we must realize that this Nr, moles per second per meter square, will be a function of R. Okay, although we are assuming steady state, because the very fact that the area itself changes. However, in R, 4 pi multiplied by 4 pi r square, which will be moles per second, or we call it W dot, this will be constant. Although the total moles per second, or kg per second will be conserved, will be constant under steady state, but kg per second per meter square or moles per second per meter square will not be a constant with R. So when we write down the expressions for Nr and in the previous expressions and we integrate, we have to ensure that we are making a correct integrations. Okay, so we can always go back and integrate the previous expressions, which we had W dot RT over 4 pi P DAB 1 over R1 minus 1 over R2 equals ln P minus PA2 over P minus PA1. Okay, so this is the expression we obtain for total moles per second of A diffusing in a spherical coordinates. We can assume that size of the sphere is very small, and when it when the naphthalene evaporates, it goes into a very large, very long distance, which means we can assume R2 in the limit very large, R2 tends to infinity. PA2 is 0 at a very far distance from here, R tends to infinity, concentration here is 0. PA1 is decided by the vapor pressure or sublimation pressure at that temperatures. Now we have our expressions for a steady state W1, which is a function of R. Now from here we have to go back to our material balance over material balance of evaporating liquid over del T. And when we write such expressions, again we have to make use of quasi steady state approximations, because every time the size of this sphere changes with time, which means the concentration gradient from the surface to this very far, which is 0, will also change with time. So in reality it's an unsteady state problem. What we are trying to make use of quasi steady state approximation.